Here we go. Now I'm recording. Okay, so yes, to get your answers in grams of CO2, and that's it. You're done. That's the problem. All right. So before we move on, because this is a really easy one, and I hope you know that. I hope you notice it's easy because look, one of them already starts you in moles, so you have to do just a one-stepper to get to the product, and then the other one is grams to moles, mole to mole ratio, and then that's it. And then the last problem is just that little one-stepper. So I hope you understand that this is really easy. This is an easy one. So does anyone have any questions on this one though before we go on?
I have a question.
What's up?
Why didn't we use the 0.86 moles of chlorine? I mean,
why did we not use it? Or
why didn't we? Why didn't we use it for the last one?
Yeah, that's a great question. Can someone answer that for her?
Because the 0.86 moles, we would never get to it because it's an excess reagent. It doesn't stop at 0.335, but we would never get to 0.86 because this is the limiting reagent in the problem. 0.335 moles of Cl2.
Right, that's absolutely right. Do you understand that, Kennedy?
Yes.
Yeah, so like we never, in the quick tutorial, if you remember, what I started like crossing out one of the reactions. I was like, you never, ever, ever, ever. Yeah, so this is the reaction that we would never, ever, ever use. Once you figure out who the limiting reagent is, then that other calculation, you forget about it. You like erase it, don't do anything with it because you never actually get to that. You never get to 0.86 moles. You can only get to 0.335 if you start out with this much starting material. I hope that makes sense. And it's, if you think about it in the sandwiches, if you can only make 3 sandwiches, then, but you had to figure out with the 2 starting materials, if I have 3 slices of ham and 2 slices of cheese, you can only make 2 sandwiches. So you never get to what the 3 slices of ham would have gotten you. You can only get to 2 sandwiches because of the limiting reagent of the cheese, if that makes sense.
Yes, it does.
Okay, cool. So, any other questions?
I have a question.
What's up?
This is a dumb question.
Great.
So, where does the 70.9 come from? Because I don't remember.
Somebody tell her. Come on.
It's the molar mass. It's the molar mass of the chlorines. You just times it. You times chlorine by 2.
Right.
Okay.
Yeah. So each chlorine is 35.45, but it's Cl2. So 35.45 times 2 will give you 70.9. I do it in my head because I use chlorine so much that I know it. So does that answer? You're good?
I'm good.
Okay. Anybody else? Okay. So I want to move on. And look at this. It's already here on the board. Yay. So this question is number 3.89. So just a couple down from 3.86. So yeah, this is 3.89. I'm going to read it, okay? It's a paragraph, but I've written the stuff down, so hopefully you guys can stay with me. Okay, so hydrogen fluoride is used in the manufacture of Freon, which Freon is really bad. It destroys the ozone layer. But anyway, hydrogen fluoride is used in the manufacture of Freon and in the production of aluminum metal. It is prepared by that reaction on the board that you see there. Here's the actual question. In one process, 6 kilograms of CaF2 are treated with an excess of sulfuric acid. Oh, I shouldn't have written there. God darn it. So again, one process, 6 kilograms of CaF2 are treated with an excess of sulfuric acid and yield 2.86 kilograms of HF. The question wants you to calculate the percent yield of HF. Okay, so a limiting reagent problem, the most important thing is that it tells you who gets used up first, right? But it also tells you other things, right? When you do these calculations, you can get other information from it. So for example, if we go back to the first one, right? This is the first one, and we figured out that HCl was the limiting reagent. I didn't ask it, but I'm gonna ask it right now. So this 0.335, right? That 0.335 moles of the product. What is that also called? When, and I'm sorry, go ahead.
The theoretical yield?
That's exactly right, right? So the yield of how much product you're going to get theoretically. So if I use 48.2 grams of HCl and I do the experiment perfectly, in theory, I should get 0.335 moles of Cl2, okay? Or however many grams that is when you use the molar mass. I should get that many moles of Cl2 perfectly, if I do it perfectly. That is the theoretical yield. Now there's another thing called an actual yield. The actual yield is okay in real life, right? So in real life, you're not perfect. So therefore, your actual yield is typically always going to be less than the theoretical in a perfect world yield, okay? So, and like I did in the quick tutorial, there is an equation that you can use. It's called percent yield equation. And the percent yield is just basically actual yield, so the actual thing that you get, over the theoretical yield, which is in a perfect world. Okay, so now let me reread the question of what they want. They want you to calculate the percent yield of HF. You start out with 6 kilograms of CaF2 and you get 2.86 kilograms of HF. So what is the 2.86? Is it the actual or is it the theoretical?
Actual.
That's right. So this is the actual yield. Okay. So what do I need? If they want to know percent yield, what's the thing that I need to figure out?
The theoretical yield.
That's right. The only other thing, the only other variable. So how do we get the theoretical yield? Somebody tell me.
Find the limiting reagent.
No. You don't have to find the limiting reagent because let me read the problem again. In one process, 6 kilograms of CaF2 are treated with an excess of sulfuric acid. So who is your limiting reagent?
CAF2.
That's right. This is already your limiting reagent. They tell you, because they tell you this is you reacted with an excess of sulfuric acid. So that must be your excess reagent. So we don't have to figure out the limiting reagent. So how do I find theoretical yield, you guys?
Would you no. I was gonna say, wouldn't you subtract
Isn't the theoretical yield the limiting reagent?
Yes, the theoretical yield comes from the limiting reagent. And just to address what it was Christian that was talking, right? Just to address what Christian was saying, you don't subtract anything, Christian, because these are different people. So I think what you were trying to do is subtract the 6 from the 2.86 or vice versa. You can't do that because those are different people. You can't subtract apples from oranges. They have to be in the same unit. So units are very, very important, right? So you don't subtract these two numbers that you see here. You have to answer the question. The question is asking, I'm asking actually, we need to get the theoretical yield of this reaction. I mean, I don't understand why this is difficult because we just did it up here. We just did it up here. So how do I get theoretical yield?
Wouldn't we just like calculate accordingly, like use CAF2, how much we have of it, and just calculate to get the same amount for HF?
Yes, you have to take the CAF2 to the product that they want. So that's what I need to do. I mean, I guess if you guys don't get that, then it's pointless for me to go through this entire thing because you guys have to conceptually understand what this question is asking, because that means that all the other ones, that these are the easy ones, because then you're not going to be able to get the harder ones that I want to do today. Do you guys understand what this is asking? I mean, do you understand why? I mean, first of all, there's nothing you can do with this number, right? The 2.86, you should never do anything with that number because that's what you actually get. That's it. That's the end. So you shouldn't even think about doing anything with that number. So the only other number that's left in this problem that they give you is the 6. So what are you going to do with the 6? Well, that's the limiting reagent. So why don't I take that limiting reagent to the product to see how much I theoretically should get? Does that make sense?
Yes.
Yeah, I know, to you, Cherish. Does that make sense to everybody?
Yes.
Are you sure? Oh my goodness. Please tell me you're sure. You're getting me stressed. You're getting me nervous here. So, okay, so then if that's the case, then it just becomes a dimensional analysis problem. I would go from kilograms to grams, grams of CAF2 to moles of CAF2, because I would use the molar mass to get to moles. And then I need to move across the reaction. So I would do a mole to mole ratio. So 1 mole, because there's 1 in front of the CAF2, of CAF2 will get me to 2 moles of HF. Once I get to 2 moles of HF, then I have to get to grams of HF. So I would do use the molar mass. 1 mole of HF is equal to, I don't know, whatever the grams are. That would be actually 20, it's about 20 grams of HF. And then convert it to kilograms, because this is in kilograms. So grams to kilograms, this is 10 to the third. Oh, my bad. This is 10 to the third. This is 1 of HF. Oh my God, sorry. And then that's it. Then I would get the answer in kilograms. This would be my theoretical yield. Okay, that would be my theoretical yield, because the limiting reagent takes you to the theoretical yield. Once I have that, and this, let me just fill this stuff in. I didn't do the molar mass because I don't know the molar mass of CAF2. Does anybody know it? Did anybody calculate it? No. Okay, doesn't matter. Whatever it is, that would be your answer if you multiply all that out. And then you would take that theoretical yield, and then how would I figure out the actual answer?
You would
Divide by.
Right. So you would take the actual yield, which is 2.86, divide, and this is kilograms, both of them, obviously, divide by this Theo answer that we would get in kilograms, multiply times 100. Oh, I didn't say that when I did the percent back there. It is times 100 because it's a percent. Multiply times 100, and that would get you your percent yield, the answer. So ask questions, because I know you guys don't understand. Some of you don't understand, so ask.
Now you're saying
I have
here.
a question.
Oh, sorry. Go ahead.
Go ahead, Cherish.
Okay. So right now you're saying to multiply by 100. So I just wanted to make sure that like we do actually multiply by the number 100 instead of 100%, because I remember in the video it said to multiply by 100%. I'm pretty sure those aren't the same thing, right? So it's just number 100.
No, yeah, it's multiplied times 100 to get percent.
Okay, yeah, I was confused because like in the video it said 100%, which is 1, and that would make sense.
That's me.
Okay.
That's me talking rubbish. That's me talking rubbish, but I meant times 100 to get a percent.
Okay. Okay. Thank you.
You're welcome.
I have a question.
What's up?
Okay, so you said that the theoretical yield, not the theoretical yield, but the limiting reagent was CAF2, right?
Correct.
We used what was given of CAF2 to find the theoretical yield,
Correct.
HF.
Correct.
Okay, I don't know why, but I thought that whatever was the limiting reagent, like the number associated with it would automatically be the theoretical yield. That's why I was confused.
No,
I get it
because-
now.
Look, okay, let me read you the problem, because it's all about understanding what the problem. Let me read it again slowly. It says, in one process, 6 kilograms of CAF2 are treated with an excess of H2SO4 and yield 2.86 kilograms of HF. So the first question that I asked before we did any of the problem is, what is that? Is that the actual yield, or is that the theoretical yield? If it says it yielded, right, so that's what they actually got, then that is not the theoretical yield. That is what they actually got with mistakes, because they're human. But I need to figure out the theoretical, because the theoretical is, in a perfect world, in a perfect lab, I don't make any mistakes, I should have gotten, actually, you know what, we should do that, we should do that calculation so that you could see that theoretical yield is going to be bigger than 2.86. It has to be bigger than 2.86 because, again, you're not perfect. So what is CAF2? That's 19 times 2 plus whatever, 19 times 2 plus 40. What is that?
78.
Okay, so that's 78. And then do this calculation. Do 6 times 1 e to the third times 2 times, do it. And then get me an answer for that.
I got 3.07.
3.07 kilograms, which I don't know if that's right, but at least that seems logical because it's more, it's a higher number than what they actually got. Oh, that's my cat again. Than what they actually got. So does that make sense, Camille? Because you have to be able to discern, to decipher, to decide what number it is that they're giving you. Is it the theoretical or is it the actual? So you got to really understand that.
Okay, so like if they were like telling us that they had the theoretical yield, they would just say that it's theoretical yield or something because they didn't actually get it. Like, how would they tell us? Like,
Yeah,
how would they let us know?
I don't know how they would tell you, because usually what they do is they tell you what they actually get. So they might have to like literally tell you. So the theoretical yield, but they wouldn't want you to do that because that's the whole point of the calculation. You see what I'm saying? But I think they would have to tell you the theoretical yield is this. Can you find out what they, I mean, there's no way for you to find out what they actually got unless they give you, that's not true. Unless they give you, because look, percent yield, look at this calculation. Percent yield has all three of them. So if they give you the percent and they give you the theoretical, then you can find the actual. So they would have to, you know, ask you for something else. I don't know. But does that help or does that make sense?
That helps.
Yeah.
Yeah.
Okay. So any other questions on this? Gordo, it's okay.
Is it hungry?
No, it's definitely not. Okay, so my Gordo, okay, do you know what Gordo means? Gordo means fatso.
Fat.
Yeah, he's a little gourd. So he's definitely not going hungry. It's just that I'm monitoring his food because he's overweight and I don't want him to get sick. Like, you know, anyway, I'm very concerned about my cat's weight. So he doesn't get all the food that he wants. So right now he's playing with one of his favorite toys, but he's really just upset that he's not getting all the treats that he used to get. But he's not going hungry. Anyway, listen to him. It sounds like I'm torturing him. But anyway, we got to move on. Any other questions? No? Okay, so I want to move on to one. That's gonna be a little bit complicated and you guys are gonna hate me. But it's this one. It's question 1.14. Nope, I'm lying. That's not right. That's not 1. Wait. Yes, it is 1.14. Yes, I'm not lying. Okay. So 114, that's the question. And this one's pretty simple, but let's see. Okay. Here it goes. It says one of the reactions that occurs in a blast furnace where iron ore is converted to cast iron is that reaction that you see on the board. Suppose that 1.64 times 10 to the third kilograms of iron, 1.64 times 10 to the third kilograms of iron are obtained. Okay, so let's stop right there. Are obtained. What is that? Actual or theoretical?
Actual.
That's right, that is actual. So that, I'm just gonna go ahead and put that there. That is actual yield. Okay, so 1.64 times 10 to the third kilograms of iron are obtained from 2.62 times 10 to the third kilogram sample of that Fe2O3. Assuming that the reaction goes to completion, what is the percent purity of Fe2O3 in the original sample? Huh. So, what do you guys want to do? So let me ask you this. Let me ask you this before we start. Am I going to do anything with the 1.64 right now?
No.
No, no. So there's only one choice, right? So you have to work with the other guy, right? Which is the FE203. So what can I do with the FE203?
You can calculate accordingly to where you try to see how many kilograms of CO2 you get out of it.
Of CO2?
Yes, 3 CO2. Is that wrong?
Whoa, well, why CO2 if they're giving you information about the iron?
Oh, my fault. Yes, iron. I'm sorry.
Yes, okay. So yes, we would go to iron. We would take that. So if this is your actual, that means that this guy right here would be, this guy right here is your limiting reagent, because obviously they don't give you any information about this guy, right? So they only give you information about the Fe2O3. So you can assume that, first of all, this guy's your limiting reagent and this guy's your excess reagent. That doesn't matter for this problem, but you can assume all of that. So that means that whatever you get over here, and if you take it to this guy, that's going to give you your theoretical. Same process as we did before, right? Okay, so let's do it. 2.62 times 10 to the third kilograms. And again, I'm just going to do this quickly because, oh, this is Fe2O3. But what do I go from kilograms to grams. And then what do? What's the next fraction? What is that thing called?
Molar mass.
Good job. I want you guys to start getting used to those names. Molar mass of Fe2O3, perfect. And then what's the next fraction called?
The mole to mole ratio.
Exactly. So we do then a mole to mole ratio, Fe2O3 to 2 moles of Fe. And then we have to take us further because they gave us the information in kilograms. So I would just do molar mass again, moles to grams of Fe. Oh, Lord. Of Fe, and then grams to kilograms. Okay, grams to kilograms is 10 to the third. That's 1. Okay, then I would get an answer, right? I would get an answer. The question asks, assuming that the reaction goes to completion, what's the percent purity in the original sample? What would I do then?
Percent yield?
Yeah, exactly. Even though it kind of sounds funny, they don't actually ask you for percent yield. You know what I mean? But that's what they're asking for. So you would have a theoretical here, you have your actual year here up there, and then you would just plug it into your percent yield equation, which is the 1.64 times 10 to the third over whatever answer you get for the theoretical, right? And then times, my bad, times 100. So same. I just want you to make sure that you see that if there's a pattern for these limiting reagent problems, pattern. Okay. Do you guys understand that? Are you guys okay with that?
Yes.
So the only difference between this problem and the previous problem is that we did the mole to mole ratio because they were asking for like a specific, like a specific element.
What do you mean? We did a mole to mole ratio here. We did it right here. Here's a mole to mole ratio.
Oh, okay. Never mind. Never mind.
Same exact thing. Same. Just that this one is just, I like using this one sometimes because the question itself, you guys get really confused with the way people ask questions, right? Somebody, oh, it's the wording, but you got to get used to it. So this one doesn't specifically ask you, I don't know, for percent yield like the other one did. This one just said, assuming that the reaction goes to completion, what is the percent purity of Fe2O3 in the original sample? So the percent purity of that would basically be the percent yield, if that makes any sense. So that's it. Same answer. Okay, cool. Are we cool? Can we move on?
Yes.
Yeah, because I got some more. I got some more up my sleeve today. So this is number 125, which I hope you notice that I'm giving you high numbers, right? Like I don't And that doesn't mean that you don't do the early ones, like the number 10 and number 15. Those are all important. You have to walk before you run. But you've got to feel comfortable and practice and do them. Even if you don't understand and you fail and you get it wrong, who cares? You have to be able to expose yourself to problems that are later more complex. Because that's how you're gonna prepare yourself for my exams, not by doing number 5 or doing number 3. You know, those are good, but you got to do other ones too, more complex ones. Okay, this one is a paragraph, you guys, and this is the one that you're probably gonna hate me for, but here we go. At least part A is easy. All right, so here we go. Aspirin, and I've given you the names, yeah. So aspirin is synthesized by reacting salicylic acid with acetic anhydride, and there's the reaction. How much salicylic acid is required to produce 0.4 grams of, 0.4 grams of aspirin, assuming the acetic anhydride is present in excess. So who's your limiting reagent?
Salicylic acid.
Salicylic, yes. So that is your limiting reagent. This guy's your excess reagent. And what do they want? Let me read it again. How much salicylic acid is required to produce that much of aspirin? How do I do this? This part's easy. You're not gonna like part B. But anyway, how do I do this?
So, I mean, they're giving us 0.400 grams of aspirin.
Mm-hmm.
So we're gonna have to. Wait, what's the asking for part A? It's asking for the limiting.
Salicylic acid. How much salicylic acid is required to produce 0.4 grams of aspirin?
You take the 0.400 grams of aspirin and you calculate it to see how many grams of salicylic acid you get.
That's it. There's only one choice. You only have one number. And the question is very direct. How much salicylic acid do you need to to get to 0.4 grams? So we're basically just going backwards. So I would take the 0.4 grams of aspirin and take it to what unit of salicylic acid?
Grams of salicylic acid.
Exactly. So that's all I'm doing. So what goes at the bottom? Grams of aspirin, because it has to cancel. What goes on the top?
Moles.
Okay, what is that thing
Of
called?
aspirin.
Molar mass, exactly. So molar mass of aspirin. And then I would do, what's the next fraction called?
Molar ratio.
That's right. So I would do in 1 mole, because it's 1 mole of aspirin, in 1 mole of ASP, there's 1 mole, I'm going to say Sally, of salicylic acid, 1 mole of Sally. Then I use molar mass. In 1 mole of Sally, there's whatever the molar mass is. 1 mole of Sally. How about Kennedy, can you do the molar mass of salicylic acid, and Cherish, you do the molar mass of aspirin, please.
Okay, I got 78.07.
You did aspirin, right?
No, I did
Oh,
Sally.
sorry. So 78.07.
Yes.
Yeah, that sounds right. The aspirin, the aspirin should be like 1.
Yeah, it's roughly 180 grams.
Yeah, that's around it. 180. Okay. Now you guys do this answer. I'm asking you to do the answer because Part B, you're gonna need to reason with yourself. So get the answer. Anybody can give me the answer.
0.7, I mean 1734. And then it's a whole bunch of eights.
That doesn't sound right. That doesn't sound right. And I think that's because actually your salicylic acid, you did wrong. That's not the right molecular mass for salicylic acid. That's C7, by the way, H6O3.
Oh, I thought that was a 2.
Yeah, my bad. It's my writing. So yeah, I think it should be like I remember 120,
138.
Oh, good. Okay, 138. There we go. Now give me the answer. So whatever, it should be a smaller number than what you gave me. You gave me like a 1.
Zero 0.306.
That sounds better. Yep, that's fine. 1.306 or 1.307, whatever, grams of salicylic acid or sally. Okay, before we go on to part B, everyone understand what we did there? All we did is take the only number that they gave us and we went to the person that they're asking for. They want to know how much grams of salicylic acid I need to react, to actually do this reaction if I'm going to get 0.4 grams of the product. So I just needed to take it back. Okay. Part B, calculate the amount of salicylic acid needed if only 74.9% of the salicylic acid is converted to aspirin. And it doesn't say it here in the problem if you're reading it, but I will add, okay, let me read one more time and then I'll add what I'm gonna add. Calculate the amount of salicylic acid needed if only 74.9% of the sally is going to be converted to the aspirin. So let me make it a little bit more clear. What they're asking is, I want to get the same amount of aspirin. Okay, I want to get the same amount of the product, but I'm only going to be using 74.9% of one of the reagents. So how can I get the same amount of product if I'm only reacting 74.9% of the reagent? And this is not even a chemistry problem. This is more of like a math problem.
You'll have to increase the amount of the reagent if it's less effective.
That's exactly right. Conceptually, that is exactly what I want you to think. That's exactly right. You have to increase the amount to be able to get the same amount of product. You have to increase the amount of the reagent if the reagent is less effective. That's exactly how I would explain it. So how do I do that? How would I get that? Anybody? It obviously has to do with the 74.9%. So let me ask you this. This first reaction that we did, that first calculation, would that be if 100% is converted?
Yes.
Yeah. I hope you're looking at my freaking face. Yep. That means if I start out with 0.306, I'm going to convert all of my salicylic acid to get 0.4, right? To get the product. So if I only want, if I'm going to now, how can I use that with the 74.9%, I guess? And I hope that you guys aren't too frustrated because this is a really, it's a mathematical thing. I'm not a math teacher, but you have to be able to conceptually think about these things.
You would set up the algebra equation where 0.36 of effective salicylic acid equals some percent times X of the of if it was 100%. I don't know if that makes sense, but it makes sense to me.
I would probably do it differently because my brain is different than yours, but that sounds like it would sounds.
Wait, I think I know what he's saying. Like, isn't that x over 100 equals 79.4 over 0.306?
So I would do, maybe this is what you guys are saying. Look what I would do, because I think you guys are going in the right direction. What I would do is I would take 0.306 and divide it by 0.749. Is that the same thing you're saying?
Yes.
Yeah. See, I'm just dumb and I don't understand when people tell me. But okay, this number, if you divide the total 100% by the amount that it's effective, the less amount of percent, it's going to get you how much more in grams you need of that reactant. So in other words, this number, if you do this, it should be a bigger number. It should be bigger than 0.306 because it has to be, because it's less effective. Because in my first section, which is funny because that's probably what I would have said if I was a student as well. When my first section, one of my students said, oh, I know, I would take the 0.306 and I would multiply it times 74.9%, times 0.749, and then I would minus it, right? And I was like, okay, let's do that. Let's do that. And so we did it, and so basically we did 0.346, oh, my bad, 0.306 times 0.749. That gave us a number. Can someone do that really quickly? It's like 0.007 or something like that.
I got 0.229.
Okay, there you go. I don't remember. 0.229. And then she said, oh, then I would take this answer and subtract it from the original 306. But if you do that, you would obviously get a smaller number than 0.306, which conceptually should not make sense to you. It should not, it will not work. Because like Justin said, if it's 74.9% as effective, then you have to have more of it. So the only way you get more of it is if you do 0.306 divided by the percent, which would give, can someone do the right way? Can someone do this and tell me what the answer is for that one?
I got 0.408.
Exactly, 0.408 grams. So you need 0.048 grams of the reactant to be able to get the same amount of product that was originally asked for, if the thing is 74% as effective, less effective, sorry. I hope I haven't really upset you guys.
I have a question.
Yes, and maybe I can't answer it, but I will try.
This is probably a dumb question, but it's just not clicking in my head. So I was gonna do like something similar to this, but using the 138 grams of salicylic acid. Like I would calculate like the 74.9% of the 138. Why wouldn't I do that? I'm confused on that.
So say, my bad, say it again.
So
why
like
would you use the 138? Tell me that thing that you said.
Why wouldn't I calculate 74.9% of 138 grams of salicylic acid?
So you're asking why you wouldn't take the molar mass, right? Because that's the molar mass. The molar mass of salicylic acid and multiply that times 74.9%. Because we're not asking you just about the molar mass, right? We're not asking you about something about that compound. We're asking you, I need to get the same amount of yield, which involves a whole entire reaction.
Oh.
Right? Yeah, that 0.306 is of the reaction. That's the reaction yield.
Okay, I got it.
Yeah, good. Any other questions? Because I know there's only 5 minutes, but I do want to try to do the last part of this and introduce another question. So any other questions about this? this is recorded, so you can go back and like pause it and think about it, because you really do need to get that. So there is actually one more part to this problem. The other part I think is easy, but let's see. It says in one experiment, so let me change colors. In one experiment, same problem by the way, sorry, so we're back here. In one experiment, 9.26 grams of salicylic acid, so now they're giving us more information, 9.26 grams of salicylic acid is reacted with 8.54 grams of acetic anhydride. Can you calculate the theoretical yield of aspirin and the percent yield if only 10.9 grams of aspirin is produced? So this is sort of like an extension. How is this easy? Does this sound easy to you? Because it sounds like a normal limiting reagent problem.
Yes.
Okay, I hope it does, because we don't have time to really go over it in detail. But first of all, do you have to take both of those purple starting materials? Do you have to take both of them to the product, or can you only just take one?
One.
Right. Obviously, you already know the limiting reagent is the same reaction, so you would only really take the 9.26 to this guy, to the aspirin. And then once, it's the same process, so we're not going to do it, but it literally is the same process as this right here. The same process, just starting with a different number, okay? So then you would take that, and then you would get an answer for, oh, wait, no, my bad, guys. It's the opposite of that. So it's actually this way. This way. You would go this way. But it's the same process backwards, right? So once you get an answer for that, you would have grams of aspirin, theoretically, what the grams of aspirin are, right? That would give you your grams of aspirin theoretical, because this 10.9 is your actual, right? So then it just said, can you get me the percent yield? Well, that's easy. The percent yield, we already have done it. Percent yield would be whatever that 10.9 is divided by whatever you get from this long reaction, this long dimensional analysis going backwards. That would be your theo times 100. Are you okay with that? This one's easy compared to the B. The B's hard, but this one's should be easy because it's the same. Are we cool with that?
Mm-hmm.
Do you want me to do it really quickly, write it down, and not ask you any questions? You want me to just write it down?
Yes, please.
Yes.
Okay. Yeah. So you would do, what the hell is it starting with? 9.26. So 9.26 grams of aspirin. I would do molar mass of aspirin. And then I would do mole to mole ratio. So mole of aspirin to mole of, what is this called? Well, God darn it, you guys, you should stop me. It's not starting with aspirin. Oh my goodness gracious. It's Sally. Sally. And then going to aspirin. And then the mole to mole ratio is 1:1. So that'd be 1:1, and then 1 mole of aspirin goes to grams of aspirin. I would then get that answer. That's my theoretical. And then I would plug it in to my percent yield equation, which the actual is the 10.9, like I wrote up there. And then the bottom would be this answer that I got right here, the theoretical times 100. That's the answer. So we're basically going backwards from the first thing that we did. The first thing we went from aspirin to Sally. This guy, we're just going Sally to aspirin, which is same but backwards. Good?
Yes.
Okay. So it's 4:30, and we're not going to do this problem. I really do want you guys to look at it because I want to talk about it before we start our molarity conversation on Monday. So on Monday, we're starting chapter 4. Like, this is it for chapter 3. But you should be able to at least think about this, and I do want to quickly go over it on Monday. So it's number 1.37. No, my bad. 137, 3.137, right? So it's 137 in the back of the book, back of the chapter. That's for the people that don't have the book, it's that reaction. And let me read the problem so you can have it on the recording. The following reaction is stoichiometric as written. And I've given you the reaction is balanced. Okay. But it is often carried out with excess NaOC2H5, right? So that's why I put the ER there. It's normally carried out in excess of NaOC2H5 to react any water that's present in the reaction mixture that might reduce the yield. Great, that seems like information I don't need. Okay. If the reaction shown was carried out with 6.83 grams of C4H9Cl, how many grams of NaO, of the other reactant, NaOC2H5, would be needed to have a 50% molar excess of that reactant? So I wrote it down on the board there. So basically, how many, if I start out with 6.83, how many grams would I need of the other reactant to have a 50% molar excess of that reactant? Think about that, because it's sort of the same, you know, process or whatever. I mean, it's easier. This is a, by the way, this is like super easy problem. Not, I don't think it's as hard as this other one that we did with the other percent. This is a lot easier. You just have to know what the hell you're doing. Know where you're going. I mean, you only really have only one choice because you only have one number. So it's deciding where to take that one number to. Okay? Do you guys have any general questions? Let me stop sharing.
So this whole week, I was in most or like all the classes, but we didn't have any Pogos, so we don't have to do a survey this week.
Correct. Thank you for saying that. We don't have to do a survey. Yep, you don't have a survey this week because we didn't do any Pogos.
All right.
Yep. Any other questions? No? Okay, so we are doing chapter 4. Start reading molarity. You should already have started chapter 4, but we're going to go over molarity on Monday. And then for real, we are going to do Pogos next week. Like we are going to do some Pogos, but not a lot, because I told you at the beginning of the semester, Pogos just takes more time, right? You need more time to actually digress and figure out the information on your own. But we're really compressed for time, and I want you guys to really get it and start thinking about it. So anyway, we're going to do Pogo, but not as many as I originally had thought. So we're going to do Pogo next week, but we're starting with molarity. So please read up on molarity and do problems. All right? If not, if you guys don't have any other questions, then I will let you go. You can go.
All right. Have a good rest of your
Thank you. Have a good day.
Have a good one.
Thank you. Bye-bye. See ya.
Subscribe to Team Makobar on YouTube. I do gaming videos.
I'm sorry, what, Christian?
Nah, I just wanted to plug my channel real quick.
Oh, sorry, they all left.
Yeah, it's all right. It's all right though. All right, have a good one.
Oh, he left. Hi.
Hi.
What's up?
So, while you were talking about the announcements, I've tried to pay again for iClicker.
Oh, hold on. Let me stop recording. Let me stop recording.